Hi everyone, welcome to the second part of my talk. In this talk, I will mention some results of mine that concern connectivity of the space of pointed hyperbolic surfaces. And the plan is to show you some continuous path in the surface, in the space, and we'll use those to show path connectivity and local connectivity of H2 dot. And if you missed the first part of my talk, H2 dot is the space of isometry classes of pointed hyperbolic surfaces with the pointed Gromov-Hausdorff topology. And this would be a typical point in my space H2 dot. And if you haven't heard of the pointed Gromov-Hausdorff topology, this is a nice topology, it's metrizable, and two pointed surfaces are close together if they look similar on a very large neighborhood from their respective base points. So in this talk, a hyperbolic surface will always be assumed to be orientable, connected, and complete without boundary. So in other words, this is a quotient of discrete torsion-free subgroups of PSL2R. So the results that I want to mention and then sketch the proofs are as follows. I show that the space H2 dot is path connected and it's also weakly locally connected. The definition is to be explained in a bit at the following points when X is a hyperbolic surface with no funnels or half planes and at the hyperbolic plane itself. So I didn't mean that it's not weakly locally connected at the other points. I simply state that it is at these 2 points, and the conjecture is that it's actually locally connected everywhere, although I haven't quite made progress along that front yet. So here are some examples of paths in the space. So one thing that you can do is you can move a base point along a fixed surface. So that seems simple enough. Another is that if you have a surface, it admits a pair of pairs decomposition, then from that we can record the Frenkel-Nielsen parameters, and then on a compact chunk of it that contains the base point, we can sort of adjust the twist and the length a little, so it could look something like this. And this is still a continuous path if you adjust those parameters in a continuous manner. Another example is that if you have a base point somewhere very far from this simple closed geodesic, then if we start pinching this curve, that means that we let the length of this simple closed geodesic go to 0. So this goes to a cusp, then this is also a continuous path. So nothing seems super surprising so far. The last one may be the least familiar one of all, which is growing a strip along a properly embedded infinite geodesic. So here's what a strip is. So we have 2 ultra-parallel geodesics in the hyperbolic disk, and then we mark a region between them. And the width of this strip can be measured using the ortho geodesic connecting the 2. And we mark one endpoint like so. So the strip has some width. And then what we want to consider is a pair of pans with 2 boundary components and 1 cusp. And this is connected to a surface on either end of this. So now what we want to do is we want to cut along this bi-infinite geodesic that exits the cusp, and then we'll glue the strip in between them. So the strip go between them with the identification so that this point is identified with this marked point, and then the identification respects the parameterization. So you sort of insert the strip along this bi-infinite geodesic. What you can do next, though, is that you can let the width vary. And now if we enlarge it more and more, so the width goes to infinity, then in the limit surface, what you will see, assuming the base point is somewhere very far from it, then you have that in the limit surface, you introduce 2 new funnels that are attached to these boundary components of the original pair of pants. So this is why I call it a construction that turns one cusp into two funnels. Similarly, you can also grow a strip that changes two cusps into a single funnel. So here's what you can do. So let's suppose you start with a surface here with a pair of pants that has two cusps with one boundary component. So this boundary component is attached to some surface, so it has some topology or not on the other side. What you can do is that you can insert a strip along this simple closed geodesic, this simple by infinite geodesic, and then let the strip grow again. So in this case, in the limit surface, you see whatever is on the left-hand side before that remains unchanged, and then you simply attach a funnel along the geodesic gamma. So now we change two cusps into a single funnel. So we see that growing strip can help us change the topology of the surface in the limit. And because this is a one parameter continuous family, we actually have introduced a path within our space. And we use this to show the following. So for path connectivity of H2 dot, so one thing that you can do, and this is a very rough sketch here, is that if you start with a surface that admits a pair of pants decomposition, you can simply move it to the middle of some pants. Then we can shrink all the boundary components into cusps. Then we grow strips along the bi-infinite geodesics connecting those cusps. And the resulting surface that you get will be a pair of pants with funnels attached to each of the boundary components. And once you get to this picture, you know that in any of these ends, the surface is unbounded. So you can move the base point out there. And in that case, the injectivity radius grows and grows, which means that the surface from that base point will look more closely like H2, right? Anything close to H2 will have a large injectivity radius. So that's one way that you can show a path from any surface to H2. And in this case, any surface, any pointed surface can be connected to H2, showing path connectivity. For local connectivity of this space, let me first recall a definition from Poisson topology. So we have that a space X is weakly locally connected at a point X if every neighborhood U of X, so this is the green set here, contains an open neighborhood V of X. So this is a nicer, smaller set, so that anything within V, any 2 points within V, lie in some connected subset of U. So the connected subset that I will use mainly here is a path. So I want to say that any 2 points in V can be connected via path that lies in U. So it might spill out a bit here, but it's still within the larger subset. So the point here is that if X is weakly locally connected at each point, then the space X is actually locally connected. So the goal that I want to have is that the space H2 dot as a whole is locally connected. So let me roughly sketch what to do at a point when the pointed surface, the underlying surface, has no funnel or half plane. In this case, we know that we can exhaust the surface completely by finite type geodesic subsurfaces. So we can sort of stratify what's close to this surface using the surfaces in the exhaustion. So let's say we pick this level xk. So any surface, any pointed surface close to this level will have to have this subsurface included. So that means that we'll work with this fixed subsurface, and then we'll show that there's a way of connecting this to its Nielsen extension. And to get funnels attached to these components, you have seen the construction of blowing one cusp two funnels and two funnels and two cusps into one funnel. So this will be used here. In another scenario, which is of H2, we have that anything that's close to H2 must have a large injective radius, right? So we can stratify our neighborhoods that we want to show is locally connected by the injective radius. The statement we want to show is that if you have UR, which is this set here, then there exists R prime, which is bigger than R, right? So that any 2 points within here can be connected. And the proof strategy that they will use is that any point that has injective radius R prime can actually be connected directly to H2 via a path within UR. So that means that the injective radius of the base point along this path never goes below R. So the proof has 2 cases here. So when X is non-compact and when X is compact. So when X is non-compact, we know that we can decompose the surface into a union of geodesic ideal polygons. And in this case, we can insert the strips along the geodesics. And then we can widen the width of the strips again and have that get closer and closer to H2. On the other hand, if we have that a surface close to H2 is compact, then what we want to do is we want to find a separate enclosed geodesic that's far from the base point, like so. And then this requires some nice little lemma. And then you want to pinch a non-separating curve as to not disturb the topology on this side, on the opposite side of the base point from gamma. So now you can work with a non-compact surface again, and then you return to the first case. So I hope I didn't go too fast in sketching out the proofs here, but thank you for your attention, and I look forward to seeing you during office hours. Thank you very much.